So our ion-dipole interaction is an attractive force between specifically an ion and a molecule that has a permanent dipole moment. So ion-dipole, right? It's between an ion and a molecule with a permanent dipole. And then the sphere of hydration is, so specifically now, like in our ion-dipole interaction, if let's say we're talking about water and all of the commonly occurring ions that we might expect to be in water, we create something called the sphere of hydration, which is a cluster of water molecules surrounding an ion in aqueous solution. And this cluster is due to the intermolecular forces that exist not only between the water molecules and the ion, but also between the water molecules and the water molecules themselves. Okay? So for example, if we look at sodium here, and I'll remind you that our water molecule has this bent geometry, right? Where it's partially negative on the oxygen side and partially positive on the hydrogen side. Water will surround itself such that the oxygens are pointing towards the cation, because the oxygen is partially negatively charged and the cation is fully positively charged. Okay? So that's our ion-dipole interaction. But now if we look, and we would call this a hydrated Na-ion, because that sodium plus ion is not like naked or anything like that, right? It's surrounded by water molecules, and as that ion moves through solution, those water molecules travel with it. Okay? So the hydrated anion, so in this case a hydrated chloride, will be surrounded by water molecules, but this time with the hydrogens oriented towards the anions, because the hydrogens are slightly positively charged and the anion is fully negative. Okay, so now as we imagine here, this simple network of molecules creates our inner sphere of hydration, okay, which is indicated here by this darker blue color. Okay, we would have an outer sphere of hydration, which is the water molecules that are interacting with the water molecules that are interacting with the ions. And then finally, we have what we would just call bulk water. And we call this bulk water because it's as if the ions are not even there. So to these water molecules that are on the very outside, it's like they can't even feel that there's a cation there. Okay? And as you might imagine, the more concentrated one of these solutions becomes in ions, the less bulk water we have. Okay, so as we get into chapter 11, we'll talk about this when we have concentrated solutions of ions. There's some very interesting properties that manifest, namely osmosis, as well as boiling point elevation and freezing point depression. So we'll talk about that soon, okay? So let's move forward here, okay? And more discussions of interactions amongst polar molecules. So here's a thought example that I want you to kind of think about on your own for a moment. So maybe pause the video for a second, but I'm just going to move right past this. So if we look at these two molecules right here, okay, 2-methylpropane and acetone. If we look at 2-methylpropane, it has 1, 2, 3, 4 carbons. So that's a C4. Acetone, on the other hand, only has 3 carbons. So why is it that acetone boils much higher than 2-methylpropane? So think about that, okay? Did you think about it? Did you pause the video? Maybe you already have the answer in your head. I'm going to keep moving forward. So the answer is the dipole moment in acetone. It's much, much stronger than the lack of dipole moment. I mean, you might be looking at this and say, well, this molecule is not symmetrical, so it should have a dipole moment, and that's true. But the dipole moment of this molecule will be incredibly weak because carbon and hydrogen don't have a lot of difference in their electronegativity. However, carbon and oxygen, right, there's a big fat dipole moment that exists between that carbon and oxygen as indicated here in this picture, right, where it's partially negative on this side and partially positive on this side. So that means neighboring acetone molecules, I'm going to use the shorthand notation of drawing this molecule. So that means neighboring acetones can line up like this, right? They're lining up with their dipole moments all in a row like soldiers in a line, okay? And that keeps them stuck to each other quite well, okay? Even so, acetone boiling at 329 Kelvin, you know, that's like 50 some odd degrees Celsius. So it's not a large boiling point per se. But all the same, it's significantly larger than 2-methylpropane's boiling point because of this dipole moment, all right? Okay, so we have so what I just described there with acetone is what we call the dipole-dipole interaction. So an attractive force between polar molecules, and the dipole moments will line up. So for example, take water, right? So we can see in a network of water molecules, they will always be aligned, oxygen, hydrogen. I could draw another one right here, right, where that dotted line is showing you that interaction, that intermolecular force interaction, okay? So, and as it turns out, the dipole-dipole interaction is incredibly strong. And we have a special name for this type of interaction, specifically when it involves hydrogen. And I'll talk about that next, okay? So we have another type of interaction, the dipole-induced dipole interaction, and it is exactly what you might think it is. It's an attraction between a polar molecule and the oppositely charged pole it temporarily induces in another molecule. So for example, if we look at water and oxygen, as it turns out, interact quite strongly, okay? And the reason for that is because as a water molecule gets close to oxygen, it can do this thing, right, where the negative end of this molecule makes these electrons move to the opposite side temporarily in the oxygen and creates this dipole-induced dipole. So why is this important? Well, as it turns out, if we imagine like a jar of water, and maybe there's like a little fish living in this water. So this is my terrible drawing of a little fishy, okay? Fish breathe oxygen underwater. Where does that oxygen come from? Well, it can get taken up into the water. And as it turns out, oxygen is very water soluble. Oxygen as a gas can remain in liquid water sustainably, okay, for long periods of time. And that's because of this dipole-induced dipole interaction. Because as oxygen is getting taken up, and oxygen gets taken up into water through little like actions like this, right? So those of you that are, maybe you have a fish tank, you know that if you agitate the surface of your water, it can influence oxygen to get taken up. Or if you just have a pump in your fish tank, right? If you just pump air straight into the water, that oxygen will stay in the water for a considerable amount of time because of this dipole-induced dipole. And of course, in natural waters, in the ocean and rivers and streams, when the surface of water is agitated through either waves or ripples or like a rock falling in the water, that influences air to get bubbled into that water, okay?